we look for observations, past observations up to today, and we try to identify if something is changing into the past. Of course, here we are making an implicit assumption. Let's assume explicit. We assume that the past is representative of the future. This is the main criticism that is addressed to historical data analysis. Still, of course, I believe, and some people believe, that data are an hard information. Sometimes there is criticism, data are uncertain, and therefore they are not an hard information. I'm trying to show you the two sides of the medal, the two faces, okay? In the hydrological community, water resources community, it prevails the convincement that data are the hardest information. And therefore, historical data analysis is a frequently used tool. Like, the flow of the Po River is decreasing. And then, let's look at the time series. What is the reason why I showed you some lectures ago this graph of the Po River with the regression line that was moving upward and downward, upward and downward? The reason is that I wanted to show that if one looks at the past, we had periods where the flow was increasing and periods where the flow was decreasing. And therefore, we have to try to understand in the future what will happen. And I used...
I think you didn't show us.
Okay, very simple. I think, okay, probably I didn't show it, but it's in the web pages. And it's here. Let me do like this. Sorry. I wanted to log out because otherwise there is some. I think it is one of these two. Let me see. Probably not this one.
Maybe it's in the last one, but you never talk about us.
Yeah, okay. Yeah, no problem. Yeah, it is a good thing that you told me. No, it's not here. Or maybe that
No, in the lecture of today, assessment of human impact.
Maybe, yeah, it's here. But this is for the, okay, this graph refers, let me show. This refers to the max flows, and the purpose of this graph was, the Po River time series is quite long, it's 90 years. And the purpose was, let's focus on windows, overlapping windows of 50 years. So we start from 1920, the first window is 1920, 1979. The second window is 1921, 1970. 50 years, it's a very long window. And therefore, if we estimate a tendency on a so long window, it's very reliable. Very often we deal with the shortest series. And therefore, this experiment shows that this is the annual max of the daily discharge, and when it's increasing is in blue, the regression line. When it's decreasing, it's in red. So basically, what is shown here is that this regression line is affected by relevant uncertainty. This is the purpose of this graph. Sometimes it's increasing, sometimes it's decreasing. And if you look at the whole series, it's difficult to say that something is changing. Let's look at the minimum flows, which is more important for water resources assessment. This was done with R, this graph. It's quite simple to do it with R. And I think on my website there is also the code for the R code. This is the minimum. And there is the convincement in people that the low flows are decreasing for climate change in the Po River. Same thing, it's red when it is decreasing and it's blue when it's increasing. And you see that there is variability during this series. So it's difficult to say that something is significantly changing. I mean, we are interested in changes that are effective on engineering design. And if you look at the whole series, you know, hard to say that it's, something is decreasing. And this is 2003, which was the huge drought, which you may remember. I think you were grown up enough. It was a wonderful summer, but still it was very dry. And after that, we had another minimum in 2007, but after 2007, and there was another year, I think, a couple of years ago, but after that, we didn't have any major drought. Okay, so why, and I'm going back now to the slide, to the subject of the slide. Why a regression line? To estimate the tendencies. Because a regression line and a linear regression. Why a linear regression? Because linear regression is robust. So let's make an example on the blackboard. Let's suppose that you have some data that you need to interpolate. And let's call them xt. And let's suppose that the data are like that. Okay, let's suppose that they are like that. And here is present. Now, there is, of course, an increase. If we estimate a linear regression, we get something like this, probably. And if I export it into the future, I get something like that. If I adopted a polynomial regression, the polynomial regression would fit these points better. So I may be tempted, because here I see something nonlinear, and then I may be tempted to say, this is clearly nonlinear. Why? Let's adopt a model, polynomial regression, that fits the point better. And indeed, if I draw here a polynomial line, I would get something like this. And then into the future, something like this. You see, the prediction is completely different. If you look at the time span of the observed data, more or less both models are fine. And I would prefer the blue one, the polynomial, because it's fitting the data better. But if I look at the predictions, they are much different. And therefore, at this stage, I need to ask myself, but what is the more reliable? Now, if I go to estimate uncertainty for these two models, there are theories helping me. For the linear regression, I have methods for estimating, besides the prediction, what are called the confidence bands. Which means that when I make my prediction, I can also identify a band, an upper band and a lower band, which is typically widening as I move into the future, because the longer the leading time, the horizon of my prediction, the higher the uncertainty. This is an intuition, of course. We can get it. If you want to predict the weather of tomorrow, we are quite sure of what's going on. If we move forward 1 month, we know that it's almost impossible to predict weather with 1 month's lead time. Uncertainty is increasing. And again, I have theories that help me. And this is called confidence band. The region between this upper line and the lower one is called confidence band, or confidence region. Let's say, I think band is correct. the confidence band, keep into account, is defined for a given confidence level, like how much I'm sure that my future prediction will be inside the band. Let's quantify my sureness in terms of probability. Usually what I want to say, I am 95% sure that my prediction will be, that the true value will be inside this prediction band, prediction confidence band. I want to say something like that because I am an engineer, I need always to quantify what I'm saying. So I want to be able to say I am 95% sure. And it's clear that if you want to be 99% sure, you have to expand the band. Okay? Again, we have tools, analytical tools that allow us, under certain assumptions, to say that for linear regression. There is linear regression theory, which you studied probably in your previous studies, which tell you how to estimate the regression line and how to estimate this confidence band for your confidence level. Usually it's 95%, what is required in design. Okay, if we do the same for the polynomial regression, what happens is that the band expands much more. So in this case, it would be something like this probably. Expands much more. Why there is this widening? More widening of the confidence band because the model counts more parameters, and more parameters means more uncertainty. We already discussed that. So from this example, you understand the importance of robustness, because it means that your prediction is more reliable at the end. Then the true value may be you're looking for may be here, okay? Or maybe here, maybe a little bit also outside what is the confidence band of the linear regression, and maybe inside the confidence band of the nonlinear regression. So you may be tempted to say, but then the nonlinear regression was better. And I would say no, because with a so large confidence band, you are not doing better. It's impossible to make a design with this prediction. It's impossible with a so large band. In the case of the linear regression, probably I can do a design, and then it may turn out that it's a bit wrong, but still I did something. So you see the importance of quantifying your uncertainty, and the importance of using a robust model. So in this case, I proved with this example what's the difference between a robust and a non-robust model, and why estimating uncertainty is important, because it also helps us to identify what is the best option. So this is also the reason why when we want to make future projections of climate or hydrological variables in general, we often use linear regression because we want a robust model. And this is why here, when I talk about historical data, I am introducing linear regression, and I would like to dedicate some time to it, to discuss it. What is linear regression? It's based on fitting a linear straight line, interpolating the data, and therefore if you have a time series, yt, y generic, river flow, rainfall, whatever is related to your design. We estimate a linear regression, which is expressed as a parametric model. Two parameters, A and B. A is intercept, B is slope, plus an error, plus a noise, I could say. The correct definition would be noise, but let's call it error. We are engineers, and therefore we are aware of the fact that the straight line does not reproduce the data perfectly in general, and therefore we introduce an error to adjust the model. And of course, the lower the error, the happier we are. Two parameters, very simple, and in order to see if there was a change, B is our main focus. If B is 0, there was no change. Like if I go back to this figure of the Po River, don't look at the regression line moving, just look at the black line, the data. You understand that if you fit a regression over this data, the slope B is not much different from 0. And in fact, also if you look at the red and blue line, you see that many times the slope is close to 0. The slope is B. So it's B our main focus. The regression, the interception of the regression, the interception A is basically the average of Y. Is close to the average. And then B is regulating the slope. Here we have two parameters to estimate. Let's see. How can we estimate it? For instance, by using an objective function. And there is a well-known theory behind it. Regression analysis is indeed very often carried out by using least squares as objective function. And there are assumptions on epsilon which condition the validity of the least square objective function. And you may remember something like your data, y, and also epsilon need to be Gaussian, for instance. I'm not sure whether Gaussian means a normal distribution or Gaussian distribution. I'm not sure whether I'm mentioning it, but it's not important for me. It's just important that you take into account that there are assumptions conditioning the validity of this inference, of this estimation. And then I'm mentioning here what I already discussed. There are inference methods for the confidence margin. So I can estimate the parameters A and B. I can say with a well-consolidated theory whether B is 0 or not. B will never be 0. When you estimate a number by using data, B will never be 0. It may be close to 0, and then you have to be able to say whether you can assume that it's 0. You can safely assume that it's 0. And this is important because in order to make your future projection, of course, the B value is important. There is a very extended literature on climate analysis that is based on regressing observed data. There are a lot of examples. I don't understand here, just 1 second, I changed the font size. I made something wrong here. So this one is 18. Okay, let me do. Understand what's going on here. Just 1 second. I think the text is I don't understand why I cannot change it, but let me check. Okay, let's forget about it. Sorry for this, and let's try to... One second. Okay, make an effort, it's just a couple of slides, make an effort to be able to read, I hope you can see it. And now we turn to models. Okay, so we consider the historical data analysis through the regression line. We didn't go into the details. In my web pages there are more details about regression analysis. Please have a look at the details as well. So this is basically, it was a synthetic treatment, but have a look at the details on the website as usual. You have to make reference to the web pages for preparing the exam. Now let's focus on the second option, which is modeling. And modeling means, as you know, using a model to fit the data and then to elaborate future projections. And you may say it is the same thing. Like regression analysis, we did the same. We fit the model on the data, and then we use the model to elaborate future projections. Indeed, here it's a bit different, because when I talk about modeling, models that are used in this context are not necessarily fitted by using historical data. They are conceived and fit by looking at the physical process, by trying to understand the physics that's going on, and the parameters are not necessarily tuned by using historical data. So what we did, to be clear, what we did for regression, what we did for IMOD, for rain for runoff models, it's not usually done with climate models. Climate models are tuned by physical consideration of the process. They are not tuned by checking their ability to reproduce the current and past climate. This is recognized by the climate literature. They say that their models are not meant to do that. They are not meant to reproduce what has been observed. They are meant to making predictions for the future. And of course this is criticized because some people say that if these models cannot reproduce what we observed, they cannot reproduce what we will observe into the future. But indeed the reasoning is that you know, it's to calibrate a climate model, to find historical data for calibrating this very complex set of processes is impossible. And therefore there is a fundamental difference. So in the historical data analysis, the historical data is the center of our focus. It's the subject of our attention. And then by looking at the historical data, we elaborate a prediction for the future. And we choose the most robust model in order to do that. When we turn about what we call modeling in this context, we forget about historical data. We just look at the process, we try to identify the best model that corresponds to our understanding of the process, and if historical data can support us in this process, this is fine. But if they cannot, they are not necessarily needed. Instead, if we move one step back, historical data analysis, historical data are a necessary requirement and the model is a consequence. In this case, the model is the requirement and the presence or not of historical data is just a detail. I hope the difference is clear. And there are some scientists who believe that models are a more reliable tool with respect to historical data. This is usually not the opinion of water resources managers and hydrologists. Usually hydrologists, they stick on data. But climate scientists, given the complexity of the process that they are studying and the impossibility in many cases to find historical data for these processes, they don't rely much on data. They rely more on models. And I had also several discussions in conferences where I was presenting some data analysis, and climate scientists said, I don't believe in this data, my models, the models are better. And in the engineering community, usually, you know, there is instead some skepticism when dealing with models. So you have to be aware of the kind of community you talk with, and keep in mind that when you turn into modeling, there are some communities that may completely discard you if your model is not validated. You know what validation is, comparison with historical data. With other community like climate scientists, if you talk about validation, they say, no, please, data are uncertain and I don't trust in them. So it's a bit of a complicated situation, but it's also interesting and fascinating because it is complicated. Okay, models, and when we talk about models, I'm sorry, it's not very easy to read, but I hope that, okay, it's available on the website. And we can divide the models of human impact in two main categories. And keep in mind, we are talking here about models that are trying to interpret the processes. Regression is not trying to do that. Regression forgets about the process. Regression can be applied to the number of potatoes, to temperature, to whatever. In this case, we are talking about mechanistic models. They look at the processes and try to interpret them. So we can split the models in two categories. Again, this is my interpretation. We are talking about models of human impact. You can consider human impact as an external forcing or as an internal part of the model. Let me provide two examples. Let's suppose that your model is the flow duration curve for making predictions. And then you want to take into account what happens if upstream will happen a water withdrawal. What would you do? Usually you take your flow duration curve. If the water withdrawal is constant, you shift the flow duration curve down of a quantity which is equal to the water withdrawal. In doing that, you have estimated the human impact through a model, and the model is just looking at the project of the water withdrawal, and then you consider the human impact as an external forcing, and you updated the flow duration curve, which is your design model, by considering the human impact. This is external forcing. Being an external forcing, it neglects what is the feedback between the human impact and the flow duration curve. It is just what is the feedback, meaning that the human impact is an external forcing, modifies the flow duration curve. The flow duration curve may, in turn, modify the human impact. This is the feedback. When we talk about feedback between climate and hydrology, it means climate is influencing hydrology. If we consider climate as an external forcing, we end up with just estimation of climate change correcting hydrology. In doing that, we ignore that changes in hydrology may feedback on the climate. And climate changes in itself. This is the feedback. If you consider any driver on a system as an external forcing, you ignore the feedback of the system on the driver. Okay? So let me be clearer. You have a system that you want to study. The system is your river, your water resources system, whatever. And you have a drive, an external forcing, a driver, which is affecting it. Okay, what we said is, fine, I need to identify the driver, I need to quantify it, and then I have to pass to the next step. I have to include this driver into the system. Okay, it can be an external forcing. Therefore, if the system is climate, the driver, sorry, and the system is hydrology, and hydrology may be a flow duration curve, for instance. The part of hydrology that is interesting for me is a flow duration curve. I may simply say, okay, let me quantify climate change in terms of reduced stream flow, and let me pass it to hydrology. Okay, and then this flow duration curve will move down to here. This is an external forcing. But what may happen is that the change in hydrology induces another change in climate. Again, this is the feedback. Two ways interaction. Let me provide to you a more practical example. Lake Urmia. But Lake Urmia, I'm not sure. Lake Aral, which is a similar, very similar example. A salt lake in the former Soviet Union was indeed very large. What they did is they dammed the rivers, reduced the flow to the lake, and the lake shrinked. Okay, one may say, fine, meaning that we stop here. No. No, because reducing the lake has decreased evaporation, less rainfall, less flow into the rivers, and again, this is the feedback. The lake reducing, and the lake disappeared. Now it's just a very tiny water pool. The feedback was between the system, lake, and the driver, rivers, through climate and rainfall. So you have these two options. And of course you may say, let me use this one because it's better, it's more detailed. But again, and today this is the tendency. There is a rich literature saying we have to consider all the feedbacks, and people discussing, like saying, this is extremely important, the feedbacks are very important. Feedback of climate on hydrology and the feedback of land use change on hydrology, whatever, we need to consider it, a lot of papers. But at the end of the story, the question remains why, how? Because how to estimate the feedback of hydrology on climate? We don't know these processes. So how to do that? And then uncertainty. Because this model becomes very complex. Uncertainty bands explode. Is the prediction reliable or not? This is the sense, the meaning of this slide. There are two lines of thought. The first is try to keep the model very simple. And let's keep the driver as external forcings, because in this way our prediction becomes more reliable and the design becomes doable. And there is a second line of thought, again, hundreds of papers, feedbacks. It's a buzzword. Buzzword means something very fashionable. Maybe that you know this term. I learned it like 1 year ago. It's a buzzword, feedback. And it's not clear how to take these feedbacks into account. And today there is a lot of interest in feedbacks between society and hydrology. So it's clear what is the effect of hydrology on society, because hydrology means water, and if you have water, society can develop. This is easy to understand. On the other hand, people recognize that society is impacting on hydrology through human impact. But how to quantify this? And how to predict how society will evolve? There are some predictions which are easy, like demographic expansion, which is not easy to be frank, but still it's quite, understandable. There are other impacts of society on hydrology that are more difficult to understand. When you build a dam, you are impacting the groundwater flow. We are still not able, in many cases, to quantify this, to predict this. Because, groundwater is something that usually we don't know. The mechanics of groundwater is pooling on.
But Professor,
Yeah.
but how much is important to do this? I mean,
No, how much it is important, you mean to consider the feedbacks?
no, yeah, because if I